Our cosmic journey begins not with a bang, but with a whisper of an eerie silence that permeates the vast, cold expanse of the universe. Imagine, if you will, standing at the precipice of existence, gazing into the profound darkness and realizing that something unseen, unheard, yet profoundly powerful is at play. It's a force so dominant, it dictates the very destiny of everything we know, every galaxy, every star, every atom. What is this cosmic accelerator that silently stretches the fabric of space-time, pushing galaxies further and further apart at an ever-increasing speed? What is this universal enigma that comprises nearly 70% of our cosmos, yet remains almost entirely beyond our grasp, a phantom limb of reality? This isn't just a scientific puzzle, it's a cosmic quest, a profound drama unfolding on the grandest stage imaginable. We are embarking on an intellectual expedition to decode the universe's greatest secret, an invisible hand guiding the ultimate fate of reality itself. From the moment of its stunning accidental discovery, this mysterious force has reshaped our understanding of cosmology, throwing decades of established theories into disarray and igniting a fervent pursuit of answers among the brightest minds on Earth. It's a story of human ingenuity and relentless curiosity, a narrative woven with threads of groundbreaking observations, perplexing contradictions, and the thrilling possibility of uncovering truths that will forever alter our perspective on our place in the cosmos.
Join us, cosmic explorers, as we delve into the heart of this profound mystery. We will unearth the clues that led to its astonishing revelation, trace its indelible mark on the grand tapestry of cosmic structure, and confront the chilling implications it holds for the universe's ultimate demise. This journey promises to be both an adventure of discovery and a drama of cosmic proportions, accessible to anyone with a spark of wonder, regardless of their scientific background. We'll navigate complex ideas like the cosmological constant, Type 1a supernovae, and the Hubble constant with clarity, transforming abstract concepts into vivid narratives. So if you're ready to explore the unseen currents that shape our universe, to confront the silent, overwhelming power that dominates all, then like and subscribe to explore this universal enigma with us. Your quest for cosmic truth begins now.
Our understanding of the universe has always been a story of gradual revelation, a slow peeling back of layers of ignorance. For centuries, humanity looked up at the night sky and saw a static, unchanging cosmos, a grand celestial sphere upon which the stars were fixed. Then, in the early 20th century, Edwin Hubble shattered this tranquil image, revealing that the universe was not static at all, but expanding. Galaxies were not merely scattered across space, they were rushing away from us and from each other at speeds proportional to their distance. This was a paradigm shift, a monumental discovery that laid the groundwork for the Big Bang Theory, suggesting a universe that began from an incredibly hot, dense state and has been expanding ever since. For decades, the prevailing wisdom held that this expansion, while ongoing, must be slowing down. Gravity, the cosmic glue, was thought to be constantly pulling everything back, gradually decelerating the expansion, perhaps even leading to a big crunch, where the universe would eventually collapse back upon itself. This was the reigning cosmic narrative, a well-established and seemingly logical progression of events. But the cosmos, as it often does, held a trump card, a startling secret waiting to be unearthed. The late 1990s saw two independent teams of astronomers embark on a mission to precisely measure the universe's deceleration rate. Their primary tool in this cosmic quest was a specific type of celestial beacon, Type 1a supernovae. These stellar explosions are not just beautiful, they are incredibly powerful and, crucially, remarkably consistent in their peak luminosity. Imagine a cosmic lighthouse, always shining with the same intrinsic brightness.
If you know how bright the lighthouse truly is, and you measure how bright it appears from a distance, you can precisely calculate how far away it is. These supernovae, exploding stars that briefly outshine entire galaxies, act as these standard candles across the vast ocean of space. By observing distant Type 1a supernovae, astronomers could measure their apparent brightness and thus their distance, and by comparing that distance to their redshift, a measure of how much their light has been stretched by the universe's expansion, indicating their recession velocity, they could map the expansion history of the cosmos. The stage was set for a refinement of existing models, a precise measurement of the universe's expected slowdown. The two teams, the Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, co-led by Adam Rees and Brian Schmid, scoured the skies, patiently accumulating data from these faint, fleeting cosmic explosions. They were looking for subtle shifts in the expansion rate over billions of years, expecting to see evidence of gravity's gentle tug. What they found, however, was anything but subtle. It was a cosmic bombshell, a discovery so profound and unexpected it sent shockwaves through the scientific community and earned them the Nobel Prize in Physics in 2011. The data, meticulously collected and painstakingly analyzed, screamed an impossible truth. The expansion of the universe was not slowing down, it was speeding up. This was like throwing a ball into the air and watching it accelerate upwards instead of falling back down. It defied all expectations, challenging the very bedrock of established cosmology. Gravity, as we understood it, pulls things together. What force, then, could be pushing the universe apart, overcoming the immense gravitational pull of all the matter within it? This was the moment of discovery for the universal accelerant, an entity that was immediately dubbed dark energy. The initial reaction among many scientists was disbelief, even skepticism. Could there be a systematic error in their measurements? Were the standard candles not as standard as presumed? But as the data was scrutinized, reanalyzed, and independently verified, the conclusion remained unwavering. Something was actively driving the universe's expansion to accelerate. This was the dawn of a new era in cosmology, one dominated by an invisible, pervasive force, silently shaping the destiny of everything. The universe, it seemed, had a hidden engine, and we had just glimpsed its enigmatic power. This profound realization marked the true beginning of our quest to understand the eerie silence of dark energy's impact.
The revelation of an accelerating universe, propelled by what we now call dark energy, thrust cosmology into an uncharted territory. If gravity was the familiar hand pulling things together, this cosmic accelerator was an invisible, pervasive anti-gravity, pushing everything apart. The immediate question was, what is it? The leading candidate, and arguably the simplest explanation, was the cosmological constant. This isn't a new concept. It was famously introduced by Albert Einstein himself in his equations of general relativity, not to explain acceleration, but to ensure a static universe, which was the prevailing belief in his time. When Hubble discovered the universe was expanding, Einstein famously called the cosmological constant his biggest blunder. Oh, the irony. What was once deemed a mistake now seemed to be the most elegant solution to the universe's accelerating expansion. The cosmological constant, often denoted by the Greek letter lambda, represents an inherent energy density of empty space itself. It's not matter, nor radiation, but a property of the vacuum, a constant pressure that doesn't dilute as space expands. Imagine empty space as not truly empty, but bubbling with virtual particles popping in and out of existence, creating a subtle, pervasive energy field. If this vacuum energy has a positive value, it would exert a negative pressure, effectively acting as a repulsive gravity. As the universe expands, more empty space is created, and thus more of this vacuum energy, leading to an ever-increasing outward push. This elegant simplicity makes it a compelling candidate. It requires no new particles, no new forces beyond what general relativity already describes. The lambda CDM model, lambda cold dark matter, which incorporates the lambda constant and cold dark matter, has become the standard model of cosmology, remarkably successful in explaining a vast array of observational data, from the cosmic microwave background to the distribution of galaxies. However, the cosmological constant isn't without its challenges, and these challenges are profound. The biggest headache for physicists is the cosmological constant problem. When theoretical physicists try to calculate the vacuum energy based on quantum field theory, their predictions are astronomically larger than what observations suggest, by a staggering 120 orders of magnitude. This discrepancy is arguably the worst prediction in the history of physics. It's like calculating the mass of the Earth and getting a number equivalent to the mass of the entire observable universe. This enormous mismatch suggests that either our understanding of quantum mechanics or gravity, or both, is fundamentally incomplete, or there's some unknown mechanism at play that screens out most of this vacuum energy. This tension fuels a vibrant debate within the scientific community and underscores the depth of the universal enigma that is dark energy.
Because of this profound problem, alternative models to the cosmological constant have emerged, pushing the boundaries of our understanding of this mysterious force. One prominent alternative is quintessence. Unlike the cosmological constant, which is fixed, quintessence proposes a dynamic energy field, one that can change over time and space. Imagine a scalar field, similar to the Higgs field, permeating the cosmos, its energy density slowly evolving. This evolving field could have an equation of state that varies, potentially explaining why its repulsive effect only became dominant relatively recently in cosmic history. If the density of quintessence slowly decreases over time, it could lead to a less extreme Big Rip scenario, or even allow for a future Big Crunch if it eventually flips its behavior. This dynamic nature offers a more flexible framework, potentially resolving some of the issues associated with a fixed cosmological constant. Other more radical alternatives venture into modified gravity theories. Perhaps these theories suggest it's not a new form of energy driving the acceleration, but rather a breakdown or modification of Einstein's theory of gravity on cosmic scales. Maybe gravity behaves differently over vast distances, becoming repulsive instead of attractive at immense scales. Or perhaps there are extra dimensions that influence its behavior. These theories often introduce new terms into Einstein's equations, attempting to explain the acceleration without invoking a separate dark energy component. For example, some models propose that gravity itself leaks into extra dimensions, altering its strength and behavior across the universe. While fascinating, these modified gravity theories often introduce their own complexities and have yet to achieve the same level of observational success as the lambda CDM model, which, despite its quantum conundrum, remains the leading framework. The challenge for all these alternative models is to not only explain the observed acceleration, but also to be consistent with all other cosmological observations. A high bar indeed. The quest to decipher the true nature of the cosmic accelerator continues, a testament to humanity's relentless pursuit of fundamental truth.
The universal enigma of dark energy isn't merely an abstract concept. Its presence has had a profound and observable impact on the grand architecture of the cosmos. Think of the universe as a vast cosmic web, woven with filaments of galaxies and colossal voids. This intricate structure, with its clusters of galaxies, superclusters, and the enormous empty spaces in between, is the result of billions of years of gravitational interplay. In the early universe, tiny quantum fluctuations in the primordial plasma, amplified by gravity, began to pull matter together, forming the seeds of future galaxies and clusters. For eons, gravity was the dominant sculptor, painstakingly molding the cosmic landscape. But then, approximately 5 to 6 billion years ago, the cosmic accelerant began to assert its dominance, its repulsive force becoming the primary driver of the universe's evolution. Consider the formation of galaxy clusters, the largest gravitationally bound structures in the universe, containing hundreds or even thousands of galaxies. These immense agglomerations grew over billions of years, drawing in matter from their surroundings. However, the accelerating expansion of the universe, driven by the mysterious force, works against this process. As space expands more rapidly, it becomes harder for gravity to pull distant matter together. Imagine trying to build a sandcastle on a beach where the sand is constantly being pulled away from you. The accelerating expansion hinders the continued growth of these superstructures. This means that the size, abundance, and distribution of galaxy clusters across the cosmos provide crucial observational tests for models of dark energy. If the expansion were slowing, we'd expect to see more massive, more numerous clusters today. But if it's accelerating, the formation of such large structures becomes increasingly challenging over time. Observational campaigns like the Dark Energy Survey and the upcoming Euclid mission are meticulously mapping the large-scale structure of the universe to precisely measure these effects. DES, using a powerful camera on a telescope in Chile, has observed hundreds of millions of galaxies, measuring their shapes and distributions to infer the underlying distribution of dark matter and how it has been influenced by dark energy. By studying gravitational lensing, the bending of light from distant galaxies by the gravity of intervening matter, scientists can map the invisible scaffolding of dark matter and, by extension, the pervasive influence of dark energy. The Euclid mission, an ESA space telescope, will go even further, creating a 3D map of billions of galaxies over a third of the sky, charting the evolution of cosmic structure with unprecedented precision. These ambitious endeavors are designed to shed light on the very nature of the universal accelerant, helping us distinguish between the cosmological constant and alternative models like quintessence. The way structures grew or failed to grow tells a compelling story about the forces at play.
The influence of this eerie silence extends even to the cosmic microwave background, or CMB, the faint afterglow of the Big Bang, which provides a snapshot of the universe when it was only about 380,000 years old. While dark energy was negligible at this early epoch compared to radiation and matter, its later dominance has subtle yet detectable effects on the CMB. The precise patterns of hot and cold spots in the CMB, meticulously mapped by missions like the Planck satellite, encode information about the universe's composition, geometry, and expansion history. For instance, the size of the acoustic peaks in the CMB power spectrum depends on the universe's curvature, which in turn is influenced by the total energy density, including the cosmic accelerator. By combining CMB data with observations of large-scale structure and supernovae, cosmologists can build a consistent picture of the universe's composition, confirming that dark energy constitutes approximately 68% of the universe's total energy density, with dark matter making up about 27% and ordinary matter a mere 5%. This overwhelming dominance of a force we barely understand is both humbling and exhilarating. It means that the universe we observe, with its dazzling galaxies and intricate cosmic web, is largely a stage set by forces unknown, subtly influenced by a pervasive energy that dictates its ultimate fate. The meticulous mapping of cosmic structure, from the distribution of galaxy clusters to the subtle anisotropies in the CMB, serves as a powerful testament to the reality of dark energy and provides the crucial empirical evidence needed to constrain its properties.
Each observation, each new map of the universe, brings us closer to understanding the silent yet profound impact of this universal enigma, and the intricate dance it performs with gravity and matter in shaping the cosmos we inhabit. The drama of discovery continues, driven by the compelling evidence written across the cosmic canvas.
The profound implications of an accelerating universe, driven by the universal accelerant, stretch far beyond the present moment, casting a long shadow over the future of the cosmos. The nature of this mysterious force dictates not just how the universe is expanding now, but its ultimate destiny. Cosmologists have envisioned several dramatic, even chilling scenarios for the universe's end, each contingent on the precise properties of dark energy, particularly its equation of state, a measure of its pressure-to-energy density ratio. This seemingly abstract number holds the key to the universe's final act, transforming what might seem like mere theoretical musings into a profound drama with cosmic stakes. The most widely accepted scenario, consistent with the cosmological constant model, is the Big Freeze, also known as the heat death of the universe. In this desolate future, the accelerating expansion continues indefinitely. Galaxies will recede from each other at ever-increasing speeds, eventually disappearing beyond our cosmic horizon, making them effectively unreachable and unobservable. The night sky, once ablaze with billions of galaxies, would become an empty, silent canvas, save for our local group of galaxies, gravitationally bound together. Stars, having exhausted their nuclear fuel, would wink out one by one, leaving behind stellar remnants like white dwarfs, neutron stars, and black holes. Over unimaginable timescales, even these remnants would decay, and black holes would slowly evaporate through Hawking radiation. Eventually, the universe would reach a state of maximum entropy, a uniform, cold, and utterly empty void, devoid of any energy gradients to support life or any processes whatsoever. Imagine a universe where all light and heat have dissipated, where the concept of time itself becomes meaningless. This eerie silence is the ultimate endpoint, a universe frozen in an eternal, lifeless equilibrium. A more extreme and frankly terrifying scenario is the Big Rip. This hypothetical fate occurs if dark energy is not a constant but has an equation of state that causes its repulsive effect to grow stronger over time. In such a scenario, the accelerating expansion would intensify to a point where the force of the expansion would overcome all other fundamental forces. First, gravitationally bound structures like galaxy clusters would be torn apart. Then, individual galaxies themselves would disintegrate. Next, stars and planets would be ripped asunder, followed by atoms themselves, as the very fabric of space expands faster than the strong nuclear force or electromagnetic force can hold matter together. Finally, in the ultimate act of cosmic unraveling, even subatomic particles would be torn apart, leaving behind a universe of isolated fundamental constituents, each lost in an infinitely expanding void. The cosmic accelerator would have become a cosmic shredder, leaving nothing but an unrecognizable residue. While current observations strongly favor the cosmological constant and thus the Big Freeze, the Big Rip remains a chilling possibility if the properties of dark energy differ even slightly from our current understanding. The existence of the universal accelerant also profoundly impacts our cosmic horizon, the boundary beyond which we cannot observe any light or information, because the universe has expanded too rapidly for that light to ever reach us. As the expansion accelerates, this horizon shrinks. Distant galaxies that we can see today will eventually cross this horizon and become forever invisible to us. This implies a future where humanity, or any future intelligent life, will have an increasingly limited view of the cosmos. Our descendants might only ever know of our local group of galaxies, isolated within an immense, unknowable void. This raises deep philosophical questions. What does it mean to understand a universe whose vastness we can no longer perceive? Does it diminish our cosmic significance, or does it amplify the preciousness of our brief window into its grand history? The ongoing efforts to precisely measure the equation of state of dark energy are therefore not just academic exercises.
They are an attempt to glimpse our ultimate cosmic fate. Missions like the Euclid mission and ground-based telescopes like the Vera C. Rubin Observatory are designed to provide the unprecedented precision needed to distinguish between a cosmological constant and more dynamic dark energy models. The drama of this scientific pursuit is palpable. Every data point, every refined measurement brings us closer to understanding the cosmic future. The fate of the universe hangs in the balance, subtly influenced by a force that whispers its secrets only through the relentless, accelerating expansion of space itself. Our human quest for cosmic truth, then, becomes a race against time, a desperate attempt to decode the ultimate destiny before the eerie silence of an ever-expanding void claims all the universe's secrets.
In the grand cosmic ballet, where galaxies twirl and cosmic structures coalesce, two invisible titans dominate the stage: dark matter and dark energy. While both are mysterious, their roles in the universe are fundamentally different, yet intricately intertwined. Dark matter, accounting for approximately 27% of the universe's total energy density, is the cosmic glue. It's an invisible form of matter that interacts with ordinary matter only through gravity. We can't see it, touch it, or directly detect it, but its gravitational pull is evident in the rotation curves of galaxies, the gravitational lensing of distant objects, and the formation of large-scale structures. Without dark matter, galaxies would simply fly apart. It provides the extra gravitational scaffolding needed to hold them together and to form the vast cosmic web. In stark contrast, dark energy, the cosmic accelerator, makes up about 68% of the universe and acts as a pervasive anti-gravity, pushing everything apart. It's the silent, relentless force that is currently winning the cosmic tug-of-war, driving the universe into an accelerating expansion. Imagine a vast, invisible hand constantly pushing on the very fabric of space itself. The interplay between these two unseen entities is a fascinating and crucial aspect of modern cosmology. In the early universe, matter and dark matter were much more densely packed. Gravity, therefore, was the dominant force, pulling matter together and allowing the formation of the first stars and galaxies. Dark energy's influence, while present, was negligible in comparison. It was a subtle undertone in the grand symphony of gravity. However, as the universe expanded and matter became more dilute, the density of ordinary and dark matter decreased. The universal enigma of dark energy, if it is indeed a cosmological constant, does not dilute. Its energy density remains constant even as space expands. This meant that eventually, at a critical point, roughly 5 to 6 billion years ago, the energy density of dark energy surpassed that of matter, both ordinary and dark. At this juncture, dark energy began to assert its dominance, transitioning the universe from a decelerating expansion, slowed by gravity, to an accelerating one. This critical shift marked a turning point in cosmic history, a moment when the eerie silence of this pervasive force began to truly dictate the universe's destiny. This shift has profound implications for galaxy formation dynamics. In a dark energy-dominated universe, the gravitational clumping of matter slows down. While gravity still pulls matter together on local scales, forming individual galaxies and galaxy clusters, the accelerated expansion makes it harder for new, larger structures to form. Galaxies that are not already gravitationally bound to each other are being pushed further and further apart. This means that future generations of galaxies are less likely to merge and form even larger structures, leading to a universe where existing galaxy clusters become increasingly isolated islands in an ever-expanding cosmic ocean. The cosmic web, once a continuously growing tapestry, becomes frozen in its current state, or perhaps even begins to unravel on the largest scales.
The ongoing quest to understand the nature of dark energy also involves meticulous efforts to precisely measure the Hubble constant, h0, which describes the current rate of the universe's expansion. This seemingly straightforward measurement has become a source of significant tension in cosmology, often referred to as the Hubble tension or H0 tension. Different methods of measuring H0 yield slightly different, statistically significant results. Measurements based on the cosmic microwave background, CMB, using the Lambda CDM model and Planck satellite data, predict a lower value for H0, around 67.4 kilometers per second per megaparsec. In contrast, direct measurements using type Ia supernovae in the local universe and other distance indicators, such as those from the SH0ES, supernovae H0 for the equation of state collaboration, yield a higher value, around 73.0 kilometers per second per megaparsec. This discrepancy, debated vigorously in scientific forums, e.g. APJ 2018, Nature Astronomy 2023, could point to new physics beyond the Lambda CDM model. It might suggest that our understanding of dark energy is incomplete, or perhaps that there's some subtle interaction between dark energy and dark matter that we haven't accounted for. Some speculative theories propose that dark energy might not be constant, but has varied in the past, or that there are additional relativistic particles contributing to the early universe's energy budget. Resolving the H0 tension is one of the most pressing challenges in cosmology today, as it could reveal fundamental flaws or missing pieces in our cosmic puzzle. The tension highlights the ongoing drama of scientific discovery, where even seemingly small discrepancies can open vast new avenues of research and push the boundaries of human knowledge. The invisible dance between dark matter and dark energy continues, and understanding its intricate choreography is paramount to unraveling the universe's greatest secrets.
The pursuit of understanding the universal enigma that is dark energy is one of the grandest scientific endeavors of our time, but it is fraught with immense observational challenges. Unlike ordinary matter or even dark matter, which exert gravitational influence we can detect, dark energy interacts with gravity in a profoundly different way, making it incredibly elusive. We cannot see it, feel it, or directly measure it in a laboratory. Our only way to infer its existence and properties is through its cumulative effect on the largest scales of the universe, its relentless, accelerating push. This requires monumental efforts, pushing the boundaries of astronomical instrumentation and data analysis. One of the primary tools in this quest is the continued study of Type 1a supernovae. These cosmic beacons, as we discussed, are essential standard candles that allow us to measure distances across vast cosmic scales. By observing their apparent brightness and redshift, astronomers can map the expansion history of the universe with precision. However, these supernovae are rare and fleeting events, requiring wide field surveys that constantly scan large portions of the sky. Missions like the Legacy Survey of Space and Time, LSST, to be conducted by the Vera C. Rubin Observatory in Chile, will dramatically increase the number of observed Type 1a supernovae, providing an unprecedented dataset to constrain dark energy models. Imagine millions of these stellar explosions illuminating the cosmic expansion history with incredible detail, helping us to distinguish between a static cosmological constant and a dynamic quintessence. Another powerful probe of this mysterious force is the study of baryon acoustic oscillations, BAO. These are fossilized sound waves from the early universe, imprinted on the distribution of matter like ripples in a pond. In the very early, hot, dense universe, sound waves propagated through the primordial plasma, creating slight overdensities and underdensities of matter. When the universe cooled sufficiently for atoms to form, these sound waves froze in place, leaving a characteristic scale in the distribution of galaxies. This characteristic scale acts as a standard ruler across the cosmos. By measuring how this ruler appears stretched at different redshifts, astronomers can determine the expansion rate of the universe at various cosmic epochs.
Surveys like the Dark Energy Spectroscopic Instrument, DESI, which is creating a 3D map of millions of galaxies and quasars, are specifically designed to precisely measure BAO, providing crucial insights into the history of expansion and the properties of dark energy.
The debate between the cosmological constant and alternative models like quintessence or modified gravity is at the forefront of cosmological research. Each model makes specific, testable predictions about how the universe should evolve, how structures should form, and how the equation of state of dark energy should behave over time. For instance, if dark energy is quintessence, its density might evolve, leading to a dynamic equation of state that is not precisely -1, the value for a cosmological constant. Future, more precise observations, such as those from the Euclid mission and the Vera C. Rubin Observatory, are designed to measure this equation of state with unprecedented accuracy, effectively acting as cosmic lie detectors, distinguishing between these competing hypotheses. If the equation of state is found to deviate from -1, it would be a groundbreaking discovery, ruling out the simplest cosmological constant model and pointing towards a more complex, evolving universal accelerant. Furthermore, the existence of this cosmic accelerator has forced cosmologists to reconsider the very concept of space-time and its properties. The idea of a vacuum teeming with virtual particles, contributing to a non-zero energy density, bridges the gap between quantum mechanics and general relativity, albeit with this massive discrepancy. The search for a deeper understanding of dark energy is thus intimately linked to the quest for a theory of everything, a unified framework that reconciles these two pillars of modern physics. Could dark energy be a manifestation of quantum gravity, or perhaps an entirely new fundamental field yet to be discovered? These are the profound questions that drive the continued exploration of this eerie silence. The cosmic quest for unification and a complete understanding of the universe's fundamental forces remains a thrilling, ongoing drama, with dark energy standing as its most tantalizing and elusive protagonist.
The Euclid mission, launched by the European Space Agency, is perhaps the most ambitious, dedicated dark energy mission to date. It will create the most accurate 3D map of the universe ever, observing billions of galaxies stretching back 10 billion years. Euclid will primarily use two complementary probes, weak gravitational lensing and baryon acoustic oscillations. Weak lensing, as mentioned before, relies on the subtle distortions of distant galaxy images caused by the gravity of intervening large-scale structures, allowing scientists to map the distribution of dark matter and understand how it evolves under the influence of dark energy. By combining these measurements, Euclid aims to achieve unprecedented precision in constraining the equation of state of dark energy, potentially distinguishing between the cosmological constant and other models with a high degree of certainty. The data from Euclid is expected to revolutionize our understanding of cosmic acceleration. Beyond these dedicated missions, future observational efforts will continue to refine our understanding. Combining data from multiple probes, supernovae, CMB, BAO, and gravitational lensing will provide the most robust constraints on the nature of dark energy, minimizing systematic errors and increasing statistical power. The scientific community is also exploring entirely new observational techniques, from probing the clustering of galaxy groups to searching for subtle anisotropies in the expansion rate across different directions in the sky. The sheer scale and complexity of these observational challenges underscore the difficulty of studying a force that is, by its very nature, an eerie silence. Yet the potential rewards, a fundamental understanding of the universe's dominant component and its ultimate fate, drive this relentless cosmic quest.
The drama of scientific discovery unfolds not in grand pronouncements, but in the painstaking collection of data, the meticulous analysis, and the relentless pursuit of precision in the face of cosmic enigma.
Our attempts to comprehend the universal enigma that is dark energy have led to the development and refinement of sophisticated cosmological models, frameworks that mathematically describe the evolution and composition of the cosmos. The most successful and widely accepted of these is the lambda CDM model. As previously discussed, this model incorporates the cosmological constant, lambda, as the source of dark energy and posits the existence of cold dark matter, CDM. It has been remarkably successful in explaining a vast array of observational data, from the precise patterns in the cosmic microwave background, CMB, radiation, the faint echo of the Big Bang, to the large-scale distribution of galaxies and galaxy clusters. The Planck satellite, for instance, has provided exquisite measurements of the CMB, which are extraordinarily well matched by the lambda CDM predictions, painting a consistent picture of a universe that is flat, accelerating, and composed primarily of dark energy and dark matter.
The profound impact of dark energy on the future of astrophysics and cosmology research cannot be overstated. This universal enigma has become the central driving force behind many of the largest, most ambitious scientific endeavors of our time. It has reshaped grant funding priorities, influenced the design of next-generation telescopes and observatories, and brought together vast international collaborations. The sheer scale of the unknown about dark energy means that it will continue to be a fertile ground for discovery for decades, if not centuries, to come. Every new observation, every refined measurement, every theoretical breakthrough will bring us closer to understanding this pervasive influence. Future research will focus on several key areas. Firstly, improving the precision of dark energy's equation of state, the W parameter, will remain a top priority. Is it precisely -1, indicating a cosmological constant? Or is there a slight deviation that points to a dynamic field like quintessence? Even a tiny deviation could have monumental implications for the universe's ultimate fate. Secondly, efforts to resolve the Hubble tension will intensify. Whether it's through identifying systematic errors in current measurements or discovering new physics beyond the lambda CDM model, solving this puzzle will undoubtedly shed new light on the nature of dark energy itself. Thirdly, the search for subtle interactions between dark energy and other components of the universe, like dark matter or even baryonic matter, will continue to push the boundaries of experimental physics. This eerie silence of dark energy's non-gravitational interaction is a profound challenge, but one that could lead to revolutionary discoveries. Finally, theoretical cosmologists will continue to develop and test new models, exploring the wildest frontiers of physics, from alternative gravity theories to the implications of dark energy within multiverse frameworks. The profound questions posed by dark energy will inspire generations of scientists, ensuring that the quest to understand this mysterious force remains at the very heart of humanity's cosmic adventure. It is a testament to the scientific method's ability to turn profound ignorance into a roadmap for future discovery, constantly pushing the boundaries of human knowledge in the face of the unknown.
The cosmic web, that intricate, vast network of galaxies, filaments, and voids, is the largest structure in the universe, and its formation and evolution are profoundly influenced by dark energy. Imagine the universe as a vast, three-dimensional spider web, with galaxies clustered along the silken strands, and enormous, relatively empty voids in between. This structure formed from tiny quantum fluctuations in the early universe, which grew under the relentless pull of gravity over billions of years. However, as dark energy began to dominate the universe's expansion around 5 billion years ago, its repulsive force started to work against gravity's efforts to build and maintain this cosmic architecture. The accelerating expansion stretches the filaments of the cosmic web,
making it harder for new matter to flow into existing gravitational potential wells and for new clusters to form. This means that the statistical properties of the cosmic web, the size and distribution of voids, the thickness of filaments, and the abundance of galaxy clusters are all sensitive probes of dark energy. By meticulously mapping the 3D distribution of galaxies and analyzing these patterns, cosmologists can infer the strength and evolution of this universal enigma over cosmic time. For instance, a stronger dark energy influence would lead to larger, emptier voids and a less connected cosmic web. The eerie silence of dark energy's pervasive influence is etched into the very large-scale structure of the cosmos, providing an unprecedented opportunity to decipher its secrets. Projects like DESI and Euclid are specifically designed to map this cosmic web with exquisite precision, searching for the subtle imprints of dark energy's unseen hand. The Big Bang nucleosynthesis, or BBN, the process by which light elements, hydrogen, helium, lithium, were formed in the first few minutes after the Big Bang, provides crucial constraints on the early universe and, indirectly, on dark energy. While dark energy was utterly negligible during the BBN epoch, due to its constant energy density being dwarfed by the much higher densities of radiation and matter, the consistency of BBN predictions with observed light element abundances is a cornerstone of the standard cosmological model. Any significant deviation would necessitate a reevaluation of the entire cosmic history, potentially impacting our understanding of how dark energy fits into that narrative. For instance, if there were unknown physics or exotic particles present during BBN that later contributed to dark energy, it could affect the predicted abundances.
The success of BBN as a cosmological probe implies that the universe's energy budget and expansion rate were as predicted by the Standard Model in its earliest moments. This consistency acts as a strong anchor for our current understanding of the universe's evolution and lends credibility to the Lambda CDM model, which elegantly incorporates dark energy as a late-time dominant component. The eerie silence of dark energy's early presence, its almost imperceptible role in the universe's infancy, contrasts sharply with its profound influence today, underscoring its unique and enigmatic nature within the cosmic timeline. It is a powerful testament to the universe's evolution, where different forces dominated different epochs, each leaving its indelible mark. The concept of entropy and the heat death of the universe are inextricably linked to the ultimate fate dictated by dark energy. Entropy is a measure of disorder or randomness in a system. The second law of thermodynamics states that the total entropy of an isolated system can only increase over time, moving towards a state of maximum disorder. In the context of the universe, the heat death scenario, which is the most likely outcome if dark energy is a cosmological constant, represents the ultimate triumph of entropy. In this future, the universe continues to expand at an accelerating rate, driven by this cosmic accelerator. Galaxies beyond our local group will recede beyond our cosmic horizon, effectively isolating us. Over unimaginable timescales, stars will exhaust their nuclear fuel, black holes will evaporate through Hawking radiation, and even elementary particles might eventually decay. The universe will become a vast, cold, empty expanse where all matter and energy are spread out to their maximum possible extent, and there are no longer any temperature or energy differences to drive any processes. It will reach a state of maximum entropy, a uniform, featureless, and eternally cold void. This is the eerie silence of ultimate cosmic quiescence, a state of perfect disorder where nothing ever happens again. This bleak but scientifically compelling future highlights the profound implications of dark energy for the ultimate fate of everything we know. It is a dramatic, albeit slow motion, end, where the relentless push of this universal enigma leads to the gradual fading of all light, all heat, and all activity, leaving behind only the cold echoes of a once vibrant cosmos.
The search for cosmic voids, those immense, largely empty regions of space that lie between the filaments of the cosmic web, offers another powerful probe into the nature of dark energy. Voids are the least dense regions in the universe, where gravity's influence is weakest. Consequently, the expansion of these regions is more directly influenced by the repulsive force of dark energy than denser areas like galaxy clusters. Imagine a giant cosmic sponge, where the holes are the voids, and the sponge itself is expanding. The expansion of these empty spaces is a direct manifestation of the underlying cosmic acceleration. By studying the size, shape, and evolution of these cosmic voids, cosmologists can gain crucial insights into the properties of dark energy. For instance, if dark energy has a more dynamic equation of state, that is, W deviates from -1, it would subtly affect how quickly voids grow and how empty they become over cosmic time. Analyzing the distribution of galaxies around voids and looking for subtle imprints of the integrated Sachs-Wolf effect within these underdense regions can provide complementary constraints on the nature of this mysterious force. The eerie silence within these vast empty stretches of the universe is not just an absence of matter. It is a profound testament to the pervasive influence of dark energy, acting as a cosmic laboratory to test our models of cosmic acceleration and the ultimate fate of the universe. It's an adventure into the emptiest corners of the cosmos, seeking clues in the profound silence.
The potential for dark energy to evolve or decay over cosmic time is a key area of theoretical investigation that could drastically alter our predictions for the universe's ultimate fate. While the cosmological constant model assumes a constant energy density for dark energy throughout time, many quintessence models propose a dynamic field whose energy density can change. If dark energy were to decay into other forms of energy or particles, its repulsive push would gradually weaken. This would slow down the accelerating expansion and potentially even allow gravity to eventually reassert its dominance, leading to a decelerating universe. This could, in principle, prevent the extreme isolation of the Big Freeze or the catastrophic tearing apart of the Big Rip, offering a more benign or even cyclical cosmic destiny.
The philosophical implications for humanity's place in a dark energy-dominated cosmos are profound and multifaceted. For centuries, our anthropocentric worldview placed humanity at the center of the universe, or at least in a privileged position of observation. The accelerating expansion, driven by this mysterious force, shatters any remaining illusions of cosmic centrality. We are not at the center, and the universe is not unfolding solely for our benefit. Instead, we are transient observers in a vast, accelerating cosmos, governed by forces largely beyond our comprehension. This humbling realization can be seen as either diminishing our significance or elevating it. On one hand, our physical insignificance in a universe dominated by dark energy is undeniable. Our planet, our solar system, our galaxy, all are infinitesimally small in comparison to the vast, expanding voids. On the other hand, our unique capacity for consciousness, for scientific inquiry, and for grappling with these profound cosmic mysteries bestows upon us a remarkable distinction. We are the universe observing itself, the only known entities capable of pondering the eerie silence of dark energy and its ultimate impact. This intellectual adventure, this quest to unravel the universe's most elusive secrets, can be seen as the ultimate expression of human purpose, a testament to our insatiable curiosity. It challenges us to find meaning not in cosmic centrality, but in the very act of seeking knowledge, of confronting the unknown, and of embracing the vast, beautiful, and sometimes terrifying drama of the cosmos.
The intricate relationship between dark energy and the fundamental forces of the universe is a topic of intense theoretical exploration. While the standard lambda CDM model assumes that dark energy, as a cosmological constant, does not interact with ordinary matter or radiation, only with space-time itself, alternative models propose more complex interactions. If dark energy were to interact, even subtly, with the strong, weak, or electromagnetic forces, it would leave distinct, measurable signatures. Imagine if the strength of gravity or the charge of an electron were to subtly vary over cosmic time, perhaps influenced by the evolving density of this universal enigma. Such variations would be extremely small, but potentially detectable with highly precise astrophysical measurements or laboratory experiments. The current absence of such detected interactions is a strong point in favor of the cosmological constant model. However, the search continues. Some theories suggest that dark energy could be mediated by a new ultralight particle, a fifth force that interacts extremely weakly with matter. Experiments searching for such forces or looking for violations of the equivalence principle, which states that all objects fall at the same rate in a gravitational field, regardless of their mass or composition, could potentially uncover subtle hints of dark energy's non-gravitational interactions. This pursuit is at the cutting edge of experimental physics, probing the fundamental nature of reality itself. The eerie silence of dark energy's direct interactions is a formidable challenge, but one that could lead to revolutionary discoveries, revealing a hidden layer of complexity in the universe's fundamental laws. It's an adventure into the unknown, seeking the faintest whispers of a force that might be more intricately woven into the fabric of existence than we currently imagine. The concept of negative pressure is central to understanding how dark energy drives the accelerating expansion of the universe. In everyday experience, pressure is usually positive. A gas inside a balloon exerts outward pressure, for example. In the context of gravity, positive pressure adds to the gravitational attraction. However, Einstein's general relativity tells us that both mass energy and pressure contribute to gravity. For a substance to exert a repulsive gravitational effect, it must have negative pressure that is sufficiently large in magnitude to overcome its positive energy density. For dark energy, specifically the cosmological constant, its pressure is equal to the negative of its energy density. P equals negative rho c squared. This means that as space expands, the energy density of dark energy remains constant, but its negative pressure effectively pulls space apart.
Conversely, if dark energy were to strengthen over time, potentially leading to a value of W less than -1, the phantom energy scenario, the universe would face an even more violent end in the Big Rip. This scenario implies that the energy density of dark energy would increase as the universe expands, a terrifying prospect where the repulsive force overwhelms all fundamental forces, tearing apart everything from galaxies to atoms. The search for observational evidence of such evolution or decay is a top priority for future missions. Even a slight deviation from W equals -1 over cosmic time could reveal the dynamic nature of this universal enigma. This is the ultimate cosmic drama, where the smallest change in a fundamental parameter could dictate whether the universe gently fades away or is violently ripped apart, with the eerie silence of dark energy's behavior holding the key to our ultimate fate. The connection between dark energy and cosmic inflation offers a tantalizing theoretical link between the universe's earliest moments and its present accelerating expansion. Both phenomena involve a period of rapid exponential expansion driven by a field with negative pressure. While the inflationary epoch occurred in the first fraction of a second after the Big Bang, and dark energy became dominant much later, the underlying physics, a scalar field generating a repulsive gravitational effect, is strikingly similar. Could dark energy be a fossil remnant of the inflationary field, a leftover potential that is only now manifesting its influence? Or perhaps both are expressions of a deeper unified cosmic field that governs the dynamics of space-time itself across all epochs. Exploring this connection could lead to a more complete picture of the universe's evolution, potentially unifying the physics of the very early universe with that of the present day. It might shed light on why the cosmological constant has such a small, non-zero value, if it is somehow related to the energy scales of inflation. This speculative yet scientifically exciting avenue suggests that the eerie silence of dark energy is not an isolated mystery, but a profound echo of the universe's fiery birth, a persistent whisper from the primordial cosmos that continues to shape our destiny. It is a grand intellectual adventure, seeking a unified narrative for the universe's entire history, from its beginning to its potential end, where the unseen forces dictate the entire cosmic ballet.
Imagine a cosmic spring that, when stretched, doesn't try to pull back, but instead pushes outwards with even greater force. This counterintuitive property is what distinguishes dark energy from all other known forms of matter and energy. While ordinary matter and radiation dilute as the universe expands, and thus their gravitational influence weakens, the energy density of dark energy remains constant. This means that its repulsive effect becomes increasingly dominant over time. This concept of negative pressure is what fundamentally drives the cosmic accelerator, leading to the accelerating expansion we observe. It's a profound and counterintuitive idea, yet it is a direct consequence of the physics required to explain the universe's observed behavior. The eerie silence of this pervasive influence is a direct result of this peculiar property, a force that silently, yet powerfully, pushes the cosmos towards an unknown destiny.
The cosmic distance ladder, a fundamental tool in astronomy, is crucial for measuring the universe's expansion rate and thus for understanding dark energy. It's a series of overlapping techniques used to determine distances to celestial objects, each step calibrated by the previous one. The first rung of the ladder involves direct geometric measurements of nearby objects using parallax, the apparent shift in an object's position due to the observer's motion. This allows astronomers to establish absolute distances to a handful of stars. The next rung uses Cepheid variable stars, whose pulsation period is directly related to their intrinsic luminosity, making them excellent standard candles for distances within our galaxy and to nearby galaxies. These calibrated Cepheids then allow astronomers to measure distances to galaxies containing Type 1a supernovae, which, as discussed, are themselves remarkably consistent standard candles, capable of probing vast cosmological distances. By measuring the apparent brightness of Type 1a supernovae in distant galaxies, astronomers can infer their distances and, combined with their redshifts, reconstruct the universe's expansion history. The accuracy of each rung on this ladder is critical. Any systematic error or uncertainty at a lower rung propagates up, impacting the precision of dark energy measurements and contributing to issues like the Hubble tension. The eerie silence of dark energy is probed through these meticulous measurements, each step on the cosmic distance ladder acting as a crucial piece of evidence in humanity's grand adventure to map the expanding cosmos. It's a monumental scientific undertaking where every carefully measured light signal from distant stars and galaxies holds a clue to the universe's deepest secret.
The concept of baryon acoustic oscillations, BAO, is another powerful cosmological probe that provides crucial information about the universe's expansion history and the properties of dark energy. BAO are effectively fossilized sound waves that propagated through the hot, dense plasma of the early universe before the formation of neutral atoms. Imagine dropping a pebble into a pond. Ripples spread outwards. Similarly, overdensities in the early universe created sound waves that traveled outwards at a characteristic speed. When the universe cooled sufficiently for atoms to form, the epoch of recombination, about 380,000 years after the Big Bang, the plasma became transparent, and these sound waves effectively froze in place. This left a characteristic imprint, a preferred scale, a standard ruler in the distribution of matter in the universe. Today, we observe this standard ruler as a slight excess of galaxies separated by a particular distance, around 490 million light-years.
By precisely measuring this characteristic scale at different redshifts, that is, at different points in cosmic history, cosmologists can determine how the universe has expanded over time. This provides a complementary and independent way to constrain the properties of dark energy. If dark energy behaved differently in the past, or if its equation of state varied, it would subtly alter the apparent size of this standard ruler at different epochs. Projects like DESI are specifically designed to map millions of galaxies to meticulously measure these baryon acoustic oscillations, offering one of the most precise ways to probe the eerie silence of dark energy and its long-term influence on the cosmic expansion. It's like using a fossilized measuring tape from the early universe to gauge the expansion of the cosmos, unraveling the secrets of its accelerating destiny. The search for cosmic voids and their connection to dark energy is a fascinating area of research that exploits the emptiest regions of the universe to probe this mysterious force. Voids are vast, underdense regions in the cosmic web, spanning hundreds of millions of light-years, where there are relatively few galaxies. They are the inverse of galaxy clusters, forming where the initial density fluctuations in the early universe were slightly lower than average. Because these regions are so empty, the gravitational pull of matter within them is very weak. This means that the expansion of voids is largely dominated by the repulsive force of dark energy.
Imagine two balloons, one filled with marbles and the other mostly empty. If both balloons are expanding, the marbles in the full one will exert a stronger gravitational pull, resisting the expansion more. The empty one, however, will expand more freely, its expansion rate more directly reflecting the intrinsic expansion of the rubber itself. Similarly, cosmic voids expand at a rate that is more sensitive to the nature of dark energy than denser regions. By studying the statistical properties of voids, their size, shape, abundance, and how they evolve over cosmic time, cosmologists can gain crucial insights into the equation of state of dark energy. Analyzing the distribution of galaxies within and around these voids provides a unique window into how dark energy has influenced the universe's large-scale structure. The eerie silence of these vast empty spaces is not truly silent. It echoes with the powerful, pervasive influence of dark energy, providing a subtle but significant clue to its ultimate nature. The speculative idea of dark energy decay offers a fascinating alternative to the conventional Big Freeze scenario. What if this universal enigma isn't a permanent fixture of the cosmos, but rather a transient phenomenon, destined to weaken or even disappear over cosmic time? If dark energy were to decay into other forms of energy or particles, its repulsive push would diminish. This would cause the accelerating expansion to slow down, potentially leading to a return to a decelerating universe, perhaps even allowing gravity to eventually cause a big crunch, a reversal of expansion leading to a cosmic collapse. Such a scenario would dramatically change the universe's ultimate fate, transforming the seemingly inevitable cosmic isolation into a temporary phase, leading to a grand, cataclysmic reconvergence. The theoretical models for dark energy decay are complex, often involving new fundamental particles or fields. Detecting evidence for such decay would be incredibly challenging, requiring even more precise measurements of the equation of state of dark energy at different cosmic epochs. A deviation from W equals -1 that systematically changes over time would be a strong indicator of such a dynamic, mysterious force. While still speculative, these ideas highlight the rich theoretical landscape surrounding dark energy and the immense implications of its ultimate behavior. The eerie silence of dark energy might be a temporary calm before a radical change, a cosmic act that could shift the destiny of everything we know. It is a compelling reminder that the universe's story might be far from over, holding more dramatic twists than we can currently imagine.
The philosophical and existential questions raised by the Big Freeze scenario
are perhaps the most chilling implications of dark energy. If the universe continues its accelerating expansion indefinitely, leading to an infinitely cold, dark, and empty cosmos, what does this mean for the long-term prospects of life and intelligence? As galaxies recede beyond our cosmic horizon, the night sky would become increasingly devoid of light, eventually leaving only our own galaxy, the Milky Way, and a few nearby companions as isolated islands in a vast, desolate sea. Stars would eventually exhaust their fuel, black holes would evaporate, and all organized structures would eventually disperse due to the relentless expansion. The universe would reach a state of maximum entropy, a uniform distribution of the lowest possible energy where no processes, no thoughts, no life could ever exist again. This is the eerie silence of ultimate cosmic death, a state of perfect quiescence and absolute thermal equilibrium. While this future is billions of years away, its scientific inevitability, if the cosmological constant model holds, forces us to confront our own transient nature. It suggests a universe that, despite its initial burst of creation, is ultimately headed towards a state of profound nothingness. This existential drama, driven by the quiet, pervasive force of dark energy, prompts deep reflection on the meaning of existence, the value of life, and the enduring human quest to understand a cosmos that may ultimately become a frozen, silent abyss.
The historical context of cosmological thought, particularly the evolving understanding of the universe's geometry, is crucial for appreciating the revolutionary impact of dark energy. For centuries, cosmological models were heavily influenced by philosophical and theological considerations, often placing humanity at the center of a finite, perhaps even geocentric cosmos. The scientific revolution gradually dismantled these anthropocentric views, but the idea of a fixed, static universe persisted for a surprisingly long time, even influencing Einstein's initial formulation of general relativity. When Hubble's observations revealed an expanding universe, it was a paradigm shift, but the universe was still conceived as a grand cosmic dance, governed by gravity, whose ultimate fate would be determined by whether there was enough matter to halt the expansion or cause a collapse. The discovery of dark energy in 1998, however, introduced an entirely new dimension to this historical narrative, a universe whose expansion is not just occurring, but is accelerating. This wasn't just a new data point. It was a fundamental reorientation of our cosmic perspective, akin to discovering that the ocean beneath your ship wasn't just flowing, but actively pushing you faster and faster into an unknown future. It resurrected Einstein's biggest blunder, the cosmological constant, from the dustbin of scientific history, giving it a profound new meaning. This historical journey, from static to expanding to accelerating, highlights the iterative, self-correcting nature of science, where new observations can overturn long-held beliefs and force a complete reevaluation of our most fundamental assumptions about reality. The eerie silence of dark energy, in this historical context, represents the latest and perhaps most profound paradox in humanity's quest to decipher the cosmos.
The challenges in reconciling quantum mechanics with general relativity are at the very heart of the cosmological constant problem, and thus deeply intertwined with the mystery of dark energy. Quantum mechanics, our incredibly successful theory for describing the microscopic world of particles and forces, predicts that empty space, the vacuum, is anything but empty. Instead, it's a seething maelstrom of virtual particles, constantly popping in and out of existence, each contributing energy to the vacuum. When physicists attempt to calculate the total energy density of this vacuum from quantum field theory, the result is an enormous number, some 120 times larger than the observed energy density of dark energy. This staggering discrepancy is the most severe fine-tuning problem in all of physics. It suggests a fundamental incompatibility or incompleteness in our current theoretical frameworks.
Either our understanding of gravity on quantum scales is profoundly flawed, or there's an unknown mechanism at play that screens out almost all of this vacuum energy, leaving behind only the tiny observed amount of dark energy. This problem, often referred to as the vacuum catastrophe, is a profound paradox that cries out for a resolution. It means that the eerie silence of dark energy, its surprisingly small magnitude, is shouting a fundamental truth about the universe that we currently lack the theoretical tools to comprehend. It's a cosmic riddle that physicists around the world are desperately trying to solve, as its answer could unlock a unified theory of quantum gravity, a holy grail of modern physics.
The concept of entropy and the arrow of time is intimately linked to the ultimate fate of the universe, driven by dark energy. The second law of thermodynamics states that entropy, a measure of disorder, always increases in an isolated system. This fundamental law gives time its arrow. Time flows in the direction of increasing disorder. In the context of the universe, the ultimate outcome of an ever-accelerating expansion, driven by dark energy, is the heat death of the universe. This is the state of maximum entropy, where all available energy has been uniformly distributed and no further work can be done. Imagine a highly ordered universe with hot stars, vibrant galaxies, and complex life. As the universe expands and cools, and as dark energy pushes everything further apart, this order gradually dissolves into disorder. Stars burn out, black holes evaporate, and all matter becomes infinitely dilute. The once vibrant cosmos becomes a vast, empty, and cold expanse, utterly devoid of any temperature or energy gradients. This is the eerie silence of maximum entropy, a universe where the arrow of time has pointed towards its ultimate, unchanging conclusion. The philosophical implications are profound. Does the universe have a purpose if its ultimate destiny is a state of absolute quiescence? This inevitable march towards disorder, propelled by the unseen hand of dark energy, raises existential questions about the meaning of existence in a cosmos destined for a silent, cold end. The gravitational lensing phenomenon is a powerful observational tool that provides crucial insights into the distribution of mass in the universe, including dark matter, and thus indirectly probes the effects of dark energy. Gravitational lensing occurs when light from a distant source, like a galaxy or quasar, is bent by the gravitational field of an intervening massive object, like a galaxy or galaxy cluster, lying along the line of sight. This bending of light can distort, magnify, or even create multiple images of the background source. The amount of bending depends on the mass of the foreground object.
By meticulously analyzing the distortions of distant galaxy shapes, known as weak gravitational lensing, cosmologists can map the distribution of dark matter across vast cosmic scales. Since dark energy influences how matter clumps and forms structures, these lensing maps provide crucial constraints on its properties. For instance, if dark energy had been stronger in the past, or if its equation of state was different, it would have inhibited the growth of these large-scale structures, leading to a different distribution of gravitational lenses. Projects like the Dark Energy Survey, DES, and the Euclid mission are specifically designed to exploit weak gravitational lensing to probe the growth of cosmic structure and thus constrain the nature of this cosmic accelerator. The subtle distortions in the light from distant galaxies are not just an aesthetic curiosity. They are profound whispers from the cosmos, revealing the unseen hand of dark energy at work, silently shaping the gravitational landscape and leaving its indelible imprint on the very fabric of space-time. The future prospects for life in a dark energy-dominated universe are, by almost all accounts, bleak in the very long term, assuming the current understanding of dark energy as a cosmological constant holds true. As the universe continues its accelerating expansion, Driven by this universal enigma, galaxies beyond our local group will eventually recede beyond our cosmic horizon, making them forever invisible and unreachable. This means that future civilizations, billions or trillions of years from now, would be confined to their own galaxy or local group, unable to observe or interact with the vast majority of the cosmos. The cosmic journey of exploration and discovery, which we are undertaking today, would become increasingly limited, eventually confined to a single galactic island in a rapidly expanding, empty sea. Furthermore, as stars exhaust their fuel and as black holes eventually evaporate, the energy sources necessary to sustain complex life would become scarcer and scarcer. The universe would grow colder, darker, and increasingly empty. The eerie silence of this pervasive influence would lead to a universe where the conditions for life become increasingly hostile, eventually disappearing altogether. This long-term prognosis raises profound questions about the ultimate purpose of life and intelligence. Is it merely a fleeting spark in a universe destined for cold, desolate isolation? While this future is unimaginably distant, it underscores the profound implications of dark energy for the very existence of conscious observers and their ability to comprehend the cosmos around them. It is a dramatic, albeit slow, unfolding of a cosmic destiny that pushes the boundaries of our existential understanding.
The debate surrounding the fine-tuning problem in cosmology, particularly as it relates to dark energy, is a testament to the profound mysteries that still confront physicists. As we've discussed, the observed value of dark energy is extraordinarily small compared to theoretical predictions from quantum field theory. This means that if dark energy is indeed vacuum energy, then there must be some unknown mechanism that precisely cancels out the vast majority of the predicted vacuum energy, leaving behind only the tiny observed amount. This requires an almost miraculous level of fine-tuning, where fundamental parameters must be set with an unimaginable precision for our universe to exist as it does. Imagine a cosmic dial that controls the strength of dark energy, and that dial had to be set to one specific, infinitesimally small number out of an astronomically vast range of possibilities for stars and galaxies to form and for life to emerge. This is the essence of the fine-tuning problem. It prompts questions. Is this fine-tuning a mere coincidence? Does it point to a deeper, yet undiscovered physical principle that dictates this value? Or does it hint at the existence of a multiverse, where our universe is simply one of many, and we happen to inhabit one with the right conditions for life? The eerie silence of dark energy's magnitude, its perplexing smallness, is one of the universe's most profound paradoxes, challenging our understanding of fundamental constants and the very nature of existence. It is a mystery that pushes the boundaries of physics, cosmology, and philosophy, begging for a deeper explanation. The interplay between dark energy, dark matter, and baryonic matter is a complex cosmic dance that dictates the evolution of the universe. Baryonic matter, the ordinary matter we can see and interact with, makes up only about 5% of the universe's mass energy content. Dark matter, accounting for about 27%, does not interact with light, but exerts gravitational attraction, providing the scaffolding upon which galaxies and galaxy clusters form. Dark energy, the dominant 68%, exerts a repulsive gravitational force, driving the accelerating expansion.
In the early universe, dark matter and baryonic matter, under the influence of gravity, began to clump together. Dark matter provided the gravitational potential wells that allowed ordinary matter to fall in and form stars and galaxies. Dark energy was present, but its influence was negligible compared to the higher densities of matter and radiation. However, as the universe expanded, the densities of matter and radiation diluted, while the energy density of dark energy remained constant if it's a cosmological constant. Around 5 billion years ago, dark energy began to assert its dominance,
its repulsive force effectively winning the cosmic tug-of-war. This transition marked a profound shift in cosmic evolution, slowing down the formation of new large-scale structures and accelerating the separation of existing ones. The eerie silence of dark energy's pervasive push is now the primary architect of the universe's future, dictating how galaxies will evolve, how cosmic structures will continue to separate, and ultimately, the distant, cold, and empty fate of everything we know. Understanding this dynamic interplay is crucial for a complete picture of our cosmic history and future.
The implications of dark energy for astrobiology are profound and often overlooked, extending beyond the mere existence of life to its ultimate prospects in an accelerating cosmos. If the universe continues its accelerating expansion, driven by this cosmic accelerator, the conditions for life will fundamentally change over vast cosmic timescales. Currently, the universe is rich with stars, providing energy for planets, and galaxies are relatively close, allowing for the potential of interstellar and intergalactic communication. However, in the very distant future, as galaxies recede beyond our cosmic horizon, the universe will become increasingly cold, dark, and empty. This means that any advanced civilizations that emerge far in the future might find themselves isolated in their local galactic island, unable to observe other galaxies, and potentially unable to launch interstellar missions beyond their own gravitationally bound group. The eerie silence of this accelerating abyss would mean a universe devoid of distant cosmic companionship or the awe-inspiring spectacle of countless galaxies. This raises intriguing questions about the cosmic bottleneck for intelligence. Could dark energy be a natural limit to how far and how long civilizations can explore and expand? It forces us to consider that the fleeting window of cosmic time during which intergalactic travel and communication are feasible might be closing, making our current epoch a unique, privileged moment in cosmic history for widespread observation and potential interaction. The ultimate fate of life, therefore, is intimately tied to the enigmatic behavior of dark energy, dictating whether cosmic civilizations will thrive and expand or eventually face an inescapable, isolated demise in a rapidly expanding, silent universe.
The ethical questions about humanity's role in a universe increasingly dominated by an incomprehensible force are both daunting and inspiring. If the majority of our universe is composed of something we cannot directly perceive or understand, and if our influence on its grand cosmic destiny is utterly negligible, what meaning do we derive from our existence? Does it diminish our aspirations, or does it heighten the urgency of our quest for knowledge? The very act of pursuing an understanding of dark energy is a testament to humanity's inherent drive to unravel mysteries, to push the boundaries of the known. It speaks to a deep-seated curiosity that transcends immediate practical concerns. Furthermore, if the universe is indeed headed towards an ultimate inescapable end, be it the Big Freeze or the Big Rip, does this impose any ethical obligations on us as the only known intelligent species capable of comprehending this fate? Should we strive to preserve knowledge, to find ways to extend the lifespan of consciousness, or to explore technological solutions that might transcend the limitations of our accelerating cosmic environment? While these questions venture into philosophy and speculation, they are directly prompted by the scientific reality of dark energy. The eerie silence of this pervasive influence forces us to confront not just the universe's destiny, but our own role within that unfolding drama, challenging us to consider our responsibilities to future generations and to the cosmic quest itself. It underscores the profound interplay between scientific discovery, existential reflection, and the ongoing human adventure to find meaning in a vast and mysterious cosmos.
The concept of cosmic inflation and its connection to dark energy represents a fascinating theoretical bridge between the very beginning of the universe and its current accelerating expansion. Inflation, a hypothesized period of incredibly rapid, exponential expansion in the first fraction of a second after the Big Bang, is thought to have been driven by a scalar field, often called the inflaton field. This field would have possessed negative pressure, similar to dark energy, causing space to expand at an accelerating rate. While the energy scales and time scales are vastly different, the underlying mechanism, a field with negative pressure driving cosmic acceleration, is strikingly analogous. Could dark energy be a lingering remnant of this inflaton field, or a related field with similar properties that simply turned on or became dominant much later in the universe's history? This idea offers a tantalizing possibility for theoretical unification, suggesting a deeper connection between the universe's earliest moments and its ultimate fate. It might even provide clues to solving the cosmological constant problem, if the value of dark energy is somehow determined by the same physics that governed inflation. This intellectual adventure seeks to weave a coherent narrative for the entire cosmic timeline, from the instant of creation to the distant future, where the eerie silence of dark energy whispers of a common origin with the universe's explosive birth. It's a compelling example of how seemingly disparate cosmic phenomena might be linked by fundamental underlying physics. The challenges in forming a complete quantum theory of gravity are intimately tied to our inability to fully understand dark energy. Our two most successful theories of physics, quantum mechanics, describing the microscopic world, and general relativity, describing gravity and the large-scale universe, are fundamentally incompatible. When we try to apply quantum mechanics to gravity, particularly at extreme scales like the very early universe or within black holes, the theories break down. The cosmological constant problem, the immense discrepancy between the theoretical prediction of vacuum energy and the observed value of dark energy, is perhaps the most striking manifestation of this incompatibility.
If we cannot reconcile these two pillars of modern physics, it means our understanding of the universe is fundamentally incomplete. A complete quantum theory of gravity, perhaps through approaches like string theory or loop quantum gravity, could potentially provide a natural explanation for the small, non-zero value of dark energy, resolving the fine-tuning problem. It might reveal that the eerie silence of dark energy is not a fundamental mystery, but a consequence of a deeper unified theory that seamlessly integrates gravity into the quantum realm. The pursuit of this grand unification is arguably the greatest challenge in theoretical physics today, and its success would undoubtedly unlock the ultimate secrets of dark energy and the very fabric of reality. It's the ultimate scientific quest, where the smallest discrepancy could lead to the grandest revolution in our understanding. The search for cosmic string relics and other exotic cosmological phenomena, while not directly tied to dark energy as its cause, could provide crucial contextual information about the early universe that might indirectly inform our understanding of this universal enigma. Cosmic strings are hypothetical one-dimensional topological defects that could have formed in the very early universe during phase transitions, similar to cracks forming in cooling ice. If they exist, they would be incredibly dense and could leave gravitational imprints on the cosmic microwave background or in the distribution of galaxies. While not a direct explanation for dark energy, the detection of such relics would dramatically alter our understanding of the universe's fundamental structure and its very early history. This new understanding could, in turn, provide novel frameworks for considering the origin and nature of dark energy. For example, if the early universe was more complex or contained additional fields, it might open up new avenues for explaining the fine-tuning of dark energy or its potential interactions. The eerie silence of dark energy forces us to consider all possibilities, even the most exotic, as we cast a wide net in our quest to understand the universe's deepest secrets. It's an adventure that compels us to look beyond the obvious, searching for the faintest echoes of cosmic events that might hold the key to the ultimate nature of reality.
The ongoing advancements in observational techniques and instrumentation are the driving force behind our progress in understanding dark energy. From the initial detection using Type Ia supernovae to the sophisticated mapping of the cosmic microwave background by Planck, and the ambitious surveys of the Dark Energy Survey, DES, Euclid, DESI, and the upcoming Vera C. Rubin Observatory, each new generation of telescopes and instruments provides unprecedented precision and breadth of data. These technological leaps allow astronomers to probe further back in cosmic time, to map larger volumes of the universe, and to detect more subtle effects that constrain the properties of dark energy. For instance, highly precise measurements of weak gravitational lensing require vast amounts of data on galaxy shapes and positions. Accurate measurements of baryon acoustic oscillations, BAO, demand large-scale 3D maps of galaxy distribution. And resolving the Hubble tension will likely require even more precise measurements of both early and late universe expansion rates. The continuous development of new camera technologies, spectroscopic capabilities, and data analysis pipelines is critical. This relentless pursuit of technological excellence is driven by the profound mystery of dark energy. The eerie silence of dark energy cannot be directly heard, but it can be deciphered through the meticulous collection and analysis of its subtle cosmic imprints, pushing the boundaries of human ingenuity and engineering prowess. It's a global scientific adventure, uniting thousands of minds and billions of dollars in a shared quest to decipher the universe's most profound secret.
The philosophical implications of an eventual Big Rip scenario are perhaps the most dramatic and existentially terrifying. If dark energy is a phantom energy with an equation of state W less than -1, its energy density would increase as the universe expands, leading to an accelerating expansion that becomes ever more violent. In this scenario, the repulsive force of dark energy would eventually overcome all fundamental forces, tearing apart progressively smaller structures. First, galaxy clusters would be unbound, then individual galaxies, then solar systems, planets, and finally, even atoms themselves would be ripped apart, leading to a singularity of infinite density in the distant future.
This would be the ultimate cosmic drama, a universe not fading into cold, silent nothingness, but ending in a spectacular, violent unraveling of the very fabric of existence. What does it mean for consciousness to exist in a universe where even the bonds holding atoms together are destined to be ripped apart? Does it imply a fundamental fragility to reality, a built-in self-destruction mechanism? This scenario, while still speculative and currently disfavored by observations, highlights the profound stakes involved in understanding the precise nature of dark energy. The eerie silence of dark energy in this context becomes a terrifying whisper of an impending cosmic catastrophe, a reminder that the universe's ultimate fate could be far more dramatic and violent than we ever imagined. It's a philosophical and scientific cliffhanger, urging us to continue our quest to understand the precise nature of this cosmic accelerator before it's too late. The potential for dark energy to reveal new fundamental physics beyond the standard model of particle physics is one of the most exciting aspects of its study. The standard model successfully describes all known particles and fundamental forces, electromagnetic, strong, and weak. But it does not include gravity, nor does it naturally accommodate the existence of dark energy or dark matter. The cosmological constant problem, in particular, strongly suggests that our current understanding of the vacuum, and perhaps of quantum gravity, is incomplete. If dark energy is indeed a new fundamental field, like quintessence,
it would imply the existence of new particles or interactions that are currently beyond the standard model. If it's a manifestation of modified gravity, it would mean that Einstein's general relativity needs revision on cosmological scales, leading to a new fundamental theory of gravity. These possibilities point to an exciting future where the study of dark energy could lead to breakthroughs on par with the discovery of the electron or the development of quantum mechanics. The eerie silence of dark energy, its elusive nature, is not a barrier to discovery, but an invitation to explore the unknown. It is a cosmic puzzle piece that, once understood, could unlock a whole new chapter in our understanding of the universe's fundamental laws and the very nature of reality. It's the ultimate scientific adventure, promising to revolutionize physics as we know it.
The fine-tuning argument for dark energy is one of the most compelling and perplexing puzzles in modern cosmology. As we've explored, the observed value of dark energy is incredibly small, almost infinitesimally close to zero, yet non-zero. If it were even slightly larger, the repulsive force would have been so dominant in the early universe that matter would never have been able to clump together to form stars, galaxies, or indeed any complex structures, let alone life. The universe would have expanded so rapidly and become so dilute that it would be a sterile, empty void. Conversely, if dark energy were slightly negative, it would have acted as an attractive force, potentially causing the universe to recollapse long ago, preventing the emergence of galaxies and life. This extraordinary precision, where the cosmic dial for dark energy seems set to an almost impossibly specific value, is the essence of the fine-tuning problem. It suggests a profound paradox. Why is our universe so perfectly tailored for our existence? Is it a remarkable coincidence? A stroke of cosmic luck? Or does it point to a deeper underlying physical principle that we have yet to discover? This conundrum fuels much of the theoretical speculation around dark energy, from the multiverse hypothesis, where countless universes with different physical constants exist and we simply live in one conducive to life, to theories that propose mechanisms for self-tuning the vacuum energy. The eerie silence of dark energy's magnitude, its inexplicable smallness, is not just a scientific problem, it's a profound philosophical challenge that forces us to question the very uniqueness of our universe and our place within its grand design. It's a mystery that could revolutionize our understanding of existence itself, posing questions that resonate deeply with human curiosity and our quest for meaning. The role of cosmic expansion in diluting matter and radiation is fundamental to understanding why dark energy has only recently become the dominant force in the universe. In the early universe, immediately after the Big Bang, the universe was incredibly hot and dense, dominated by radiation, photons, and neutrinos. As the universe expanded, the energy density of radiation decreased rapidly, proportional to 1/A4, where A is the scale factor representing the size of the universe, because both the number density of photons decreased and their wavelengths stretched due to expansion, causing their energy to drop. Matter, both baryonic and dark matter, also diluted as the universe expanded, but at a slower rate, proportional to 1/A3, because only its number density decreased.
Because radiation diluted faster than matter, the universe eventually transitioned from being radiation-dominated to matter-dominated. This allowed gravity to begin forming the large-scale structures we see today. However, dark energy, if it is a cosmological constant, has an energy density that remains constant as the universe expands. This means that while matter and radiation continued to dilute, the relative contribution of dark energy steadily increased. Around 5 billion years ago, the energy density of dark energy finally surpassed that of matter, leading to the onset of the accelerating expansion we observe today. This cosmic timeline, from radiation to matter to dark energy dominance, is crucial for understanding the universe's evolution and why we exist in this particular epoch. The eerie silence of dark energy's constant presence, patiently waiting for its moment to assert its dominance,
is a profound testament to its unique nature within the cosmic energy budget, steadily and subtly reshaping the entire universe. The fascinating concept of cyclic universe models offers a dramatic alternative to the seemingly inevitable end scenarios predicted by current dark energy understanding. Instead of an eternal expansion leading to a big freeze or big rip, cyclic models propose that the universe undergoes an endless series of big bangs and big crunches, a continuous cycle of expansion, collapse, and rebirth. In some of these models, dark energy plays a crucial, though sometimes paradoxical, role. It might drive the expansion phase, but then a mechanism would need to exist to reverse its repulsive effect, allowing gravity to eventually pull the universe back together for a new big crunch and subsequent big bang. These models often involve new physics, such as extra dimensions or modifications to gravity, and are highly speculative. For example, some brain world models propose that our universe is a three-dimensional brain floating in a higher dimensional bulk, and collisions or interactions between brains could trigger these cycles. The very existence of dark energy would need to be recontextualized within such a cyclic framework, perhaps as a temporary manifestation of the universe's fundamental dynamics rather than a constant, immutable force. While still firmly in the realm of theoretical physics, cyclic models offer a captivating alternative to a universe with a single beginning and end. They suggest that the eerie silence of dark energy's current influence might just be a fleeting phase in an eternal, grand cosmic dance, a relentless cycle of creation and destruction, driven by forces we are only just beginning to contemplate.
The cosmic age problem refers to the challenge of ensuring that the age of the universe, as calculated from cosmological models, is consistent with the age of the oldest observed objects within it. Before the discovery of dark energy, cosmologists faced a dilemma. Based on the measured Hubble constant and the amount of matter in the universe, the calculated age of the universe often turned out to be younger than some of the oldest observed stars in globular clusters. This was a clear sign that something was amiss with the prevailing models of a decelerating universe. The inclusion of dark energy elegantly resolved this problem. By driving the accelerating expansion, dark energy effectively made the universe older than it would have been if its expansion had been steadily decelerating. Imagine a runner who starts fast, slows down, and then suddenly speeds up again. Their average speed might be lower than someone who keeps accelerating the whole time. In the cosmic analogy, the accelerating phase allows the universe to stretch out its expansion over a longer period, resulting in an older age consistent with stellar observations. The eerie silence of dark energy's pervasive influence thus didn't just explain cosmic acceleration, it also elegantly resolved a long-standing puzzle about the universe's age, reinforcing its crucial role in our standard cosmological model. It was a remarkable demonstration of how a seemingly inexplicable phenomenon could suddenly bring coherence to multiple disparate observations, solidifying our understanding of the universe's timeline. The search for variations in fundamental constants is a highly sensitive probe that could potentially reveal interactions with dark energy or the presence of a dynamic quintessence field. If dark energy is a scalar field that permeates the universe, it could, in principle, couple to other fundamental fields, leading to subtle variations in the values of physical constants over cosmic time and space. Imagine if the strength of the electromagnetic force or the mass of an electron were slightly different in the early universe compared to today, or subtly varied in different regions of space due to the presence of an evolving dark energy field.
Astronomers use precise spectroscopic measurements of distant quasars to look for such variations. By analyzing the absorption lines in the spectra of light from these ancient luminous objects, they can search for tiny shifts that would indicate a change in fundamental constants over billions of years. For example, the fine structure constant, alpha, which governs the strength of electromagnetic interactions, has been a particular focus.
While current observations generally place stringent limits on such variations, even a tiny statistically significant deviation could provide compelling evidence for a dynamic dark energy or a connection to new fundamental physics beyond the standard model. The eerie silence of dark energy's direct interaction is being probed by these incredibly subtle and precise measurements, listening for the faintest whisper of its influence on the very laws that govern the cosmos. It's a scientific adventure at the frontier of observational capabilities, seeking clues to the universe's most profound secrets in the fundamental constants themselves. The cosmological principle, a foundational assumption in modern cosmology, states that on sufficiently large scales, the universe is homogeneous, looks the same everywhere, and isotropic, looks the same in all directions. This principle allows us to describe the universe using simplified models and extrapolate observations from our local region to the entire cosmos. However, the presence of dark energy does not violate the cosmological principle, but rather accentuates its implications. If dark energy is indeed a cosmological constant, its uniform energy density ensures that the universe remains homogeneous and isotropic even as it accelerates. Its pervasive influence is felt equally in all directions and at all points in space. However, some alternative modified gravity theories that attempt to explain cosmic acceleration without invoking dark energy might subtly violate the cosmological principle on very large scales, leading to slight anisotropies or inhomogeneities that could be detected by future ultra-precise surveys. Similarly, some extreme models of quintessence with spatially varying energy densities could also lead to violations. The consistency of current observations with the cosmological principle and the highly uniform nature of the cosmic microwave background lend strong support to the idea of a uniformly distributed dark energy like the cosmological constant. The eerie silence of dark energy's even distribution across the cosmos is a testament to the simplicity and elegance of its nature within the standard model. But it is also a feature that future, more precise observations will continue to probe, pushing the boundaries of the cosmological principle itself. It's an ongoing dialogue between fundamental assumptions and precise observations, constantly refining our understanding of the universe's largest-scale structure.
The potential for a phase transition in dark energy is one of the most intriguing and speculative ideas, suggesting a dramatic shift in the universe's future. What if dark energy isn't a constant or even a smoothly evolving field, but something that could suddenly change its properties, undergoing a phase transition like water turning into ice? Such a transition could fundamentally alter the universe's expansion rate, leading to entirely new cosmic destinies. For example, if dark energy were to transition to a state with zero or even positive pressure, the accelerating expansion could cease or even reverse, potentially leading to a big crunch. Conversely, a transition to a stronger negative pressure state could accelerate the universe towards an even more violent big rip. These doomsday scenarios are highly theoretical and currently unsupported by observations, but they highlight the profound consequences of a dynamic dark energy that is not bound by a simple cosmological constant. Such phase transitions might be triggered by fundamental physics at extremely high energies or densities, or by the universe reaching a particular age or size. The search for any observational anomalies that could hint at such a transition is ongoing, though incredibly challenging. The eerie silence of dark energy today might be a temporary calm before a dramatic cosmic storm, a fundamental shift in the very forces that govern reality. This idea adds a layer of unpredictable drama to the cosmic narrative, suggesting that the universe's ultimate fate might not be as predictable as we currently assume.
and that an entirely new act in the cosmic play could still unfold. It's a scientific adventure into the realm of radical possibilities, pushing the very limits of our cosmic imagination. The role of computer simulations in dark energy research is absolutely indispensable. Given the vast scales and immense complexity of the universe, and the subtle, elusive nature of dark energy, direct experimentation is impossible. Instead, cosmologists rely heavily on sophisticated numerical simulations to test theoretical models and interpret observational data. These simulations, often running on supercomputers for thousands of hours, evolve a virtual universe from its initial conditions after the Big Bang, incorporating the known laws of physics, the properties of dark matter, and the hypothesized behavior of dark energy.
By varying the parameters of dark energy, such as its equation of state or its potential interactions, scientists can run different simulations and compare their outputs. For example, the large-scale distribution of galaxies, the growth of galaxy clusters, the gravitational lensing patterns, with actual observational data. This allows them to constrain which dark energy models are consistent with the observed universe and which are ruled out. For example, simulating how the cosmic web develops under different dark energy scenarios helps researchers interpret the maps created by surveys like Euclid and DESI. These simulations are our virtual laboratories, allowing us to explore the dramatic consequences of different dark energy properties on the cosmic evolution. The eerie silence of dark energy's influence is precisely mapped and modeled in these digital universes, allowing us to virtually peer into the future and past of our cosmos, and to decipher the subtle imprints of this pervasive force on the universe's grand architecture. It's a testament to the power of computational science in unlocking the universe's deepest secrets.
The cosmic age discrepancy before the discovery of dark energy was a significant puzzle, highlighting the limitations of our understanding of the universe's expansion history. For a time, astronomers faced the embarrassing problem that the calculated age of the universe, based on the measured Hubble constant and the assumption of a decelerating universe, seemed to be younger than some of the oldest stars observed in globular clusters. These ancient stellar populations, with ages estimated around 13–14 billion years, simply shouldn't have existed in a universe that was, according to the then prevailing models, only 8 to 12 billion years old. This was a clear sign that something fundamental was missing from our cosmological framework, a tension between observational data and theoretical prediction. The discovery of dark energy and the accelerating expansion elegantly resolved this cosmic age problem. By revealing that the universe's expansion has been speeding up over the past 5 billion years, dark energy effectively stretched out the cosmic timeline. Imagine a journey where you start slowly, pick up speed, and then accelerate even faster towards the end. The total time taken for that journey would be longer than if you had simply decelerated steadily from the beginning. Similarly, the accelerating expansion meant that the universe took longer to reach its current size, pushing its calculated age past that of the oldest stars, and bringing consistency back to the cosmic narrative. The eerie silence of dark energy didn't just explain the baffling acceleration, it also provided a crucial piece of the puzzle that allowed us to coherently understand the entire cosmic timeline, from the Big Bang to the present day, solidifying our understanding of the universe's history and its future. It was a remarkable demonstration of how a single, profound discovery could untangle multiple, seemingly unrelated cosmic mysteries. The search for cosmic echoes of dark energy through gravitational waves represents an exciting new frontier in cosmology. Gravitational waves, ripples in space-time itself, are generated by violent cosmic events like merging black holes and neutron stars.
With the advent of gravitational wave observatories like LIGO and Virgo, we now have a new window into the universe, complementing traditional electromagnetic astronomy. While dark energy does not directly emit gravitational waves, its presence and properties subtly affect how gravitational waves propagate across cosmic distances.
For example, the accelerating expansion caused by dark energy stretches space-time, which in turn stretches gravitational waves as they travel, causing a redshift in their frequency. By precisely measuring the redshift of gravitational waves from known sources and comparing it to their apparent distance, scientists could potentially gain independent constraints on the expansion history of the universe and, by extension, the properties of dark energy. Furthermore, if dark energy interacts with gravity in unexpected ways, as in some modified gravity theories, it could subtly alter the speed or polarization of gravitational waves, providing a unique signature. The eerie silence of dark energy might not be entirely silent to the ears of gravitational wave detectors, offering a faint but profound echo of its pervasive influence on the very fabric of space-time. This new observational frontier holds immense promise for unlocking deeper secrets about this universal enigma and the fundamental nature of gravity itself. The cosmic neutrino background, CNB, the relic neutrinos from the Big Bang, offers another potential, albeit incredibly challenging, probe into the early universe and indirectly into dark energy. Just as the cosmic microwave background, CMB, is the afterglow of photons from the early universe, the CNB is the afterglow of neutrinos, which decoupled from the primordial plasma much earlier, when the universe was only about 1 second old. These neutrinos carry information about the conditions of the universe at that very early epoch. While dark energy was completely negligible at the time of neutrino decoupling, its contribution to the overall energy density of the universe today impacts the overall expansion history, and thus how we extrapolate information from the early universe to the present. Precise measurements of the CNB, if ever achieved, could provide independent constraints on the number of relativistic particles in the early universe, the expansion rate during that era, and potentially reveal subtle deviations from the standard cosmological model that might hint at new physics relevant to dark energy. The eerie silence of these elusive neutrinos, barely interacting with matter, mirrors the elusiveness of dark energy itself. Though extremely difficult to detect, their study represents a frontier of cosmological research, offering the potential to connect the universe's earliest moments with its accelerating present, and further refining our understanding of the cosmic accelerator's ultimate role.
The future of quantum field theory and dark energy is inextricably linked. The cosmological constant problem, the immense discrepancy between the quantum mechanical prediction of vacuum energy and the observed value of dark energy, is perhaps the greatest outstanding challenge in theoretical physics. It's a gaping wound in our understanding of how quantum mechanics and general relativity fit together. Resolving this problem is paramount for a complete theory of everything. New theoretical approaches in quantum field theory and quantum gravity, like string theory or loop quantum gravity, aim to provide a more fundamental understanding of space-time and its inherent energy. These theories might naturally explain why the vacuum energy is so small, or why it has the specific non-zero value we observe as dark energy. They might also offer mechanisms for how dark energy could evolve or interact with other fields beyond what the simple cosmological constant model predicts. The eerie silence of dark energy's magnitude, its perplexing smallness, is not a sign of its unimportance, but a profound hint that there is a deeper layer of reality, a more fundamental theory, waiting to be discovered. The breakthroughs that solve the cosmological constant problem could revolutionize our understanding of quantum mechanics, gravity, and the very nature of spacetime, making the study of dark energy a central driver for the next generation of theoretical physics. It's a relentless intellectual adventure, pushing the boundaries of human thought to decipher the most fundamental laws of the universe. The ethical considerations regarding resource allocation in dark energy research are a subtle yet important aspect of modern cosmology. Projects designed to study dark energy, such as large-scale galaxy surveys, new space telescopes, and powerful supercomputing facilities, often involve massive international collaborations and billions of dollars in funding. This raises questions about prioritizing scientific endeavors. Is investing so much in understanding a force that is fundamentally incomprehensible and seemingly beyond our influence the best use of limited resources, especially when there are pressing terrestrial challenges?
However, the pursuit of dark energy is not just about understanding a cosmic curiosity. It's about pushing the boundaries of fundamental knowledge. The technological advancements, computational techniques, and collaborative frameworks developed for dark energy research often have unforeseen benefits for other scientific fields, and even for society at large. More importantly, the human drive to understand our universe, to unravel its deepest mysteries, is a fundamental aspect of our intellectual and cultural heritage. The eerie silence of dark energy is a profound challenge, a cosmic riddle that inspires generations of scientists and engineers. Investing in this kind of fundamental research ultimately enriches human knowledge, expands our intellectual horizons, and provides a powerful example of humanity's boundless curiosity. It's an investment in the very spirit of human inquiry, a recognition that the quest for cosmic truth is an inherent part of our shared human adventure. The Big Bang theory itself is remarkably robust and well supported by observational evidence, and the discovery of dark energy has refined it rather than refuted it. The Big Bang describes the hot, dense origin of the universe and its subsequent expansion and cooling. Key pieces of evidence include the expansion of the universe, Hubble's law, the existence and properties of the cosmic microwave background, CMB, the abundance of light elements, hydrogen, helium, lithium, formed in Big Bang nucleosynthesis, BBN, and the observed evolution of galaxy populations over cosmic time.
The role of dark energy is to explain the accelerating phase of this expansion, a relatively late-time phenomenon that began about 5 billion years ago. It doesn't negate the initial expansion from the Big Bang, nor does it invalidate the early universe physics described by BBN or the CMB. Instead, it adds a crucial, dominant component to the universe's energy budget that dictates its dynamics in the current and future epochs. Think of it as adding a new, powerful engine to a ship that was already moving. The ship's initial journey still happened, but its recent and future trajectory is now fundamentally changed. The eerie silence of dark energy has completed our cosmic narrative, explaining why the universe is not just expanding, but doing so with increasing speed, providing a more complete and coherent picture of our cosmic past, present, and future. It's a testament to the adaptability and strength of the Big Bang model, capable of incorporating new, profound discoveries.
The anthropic principle is a fascinating, if sometimes controversial, concept that attempts to address the fine-tuning problem of dark energy and other fundamental constants. The weak anthropic principle states that the universe's fundamental constants must be consistent with the existence of conscious observers. In other words, we observe the values of constants that we do because if they were significantly different, we wouldn't be here to observe them. For dark energy, this means that its extraordinarily small, non-zero value is precisely what allows for the formation of galaxies, stars, and planets, and the billions of years necessary for life to evolve. If dark energy were much stronger, the universe would have expanded too rapidly for matter to clump. If it were negative and strong, the universe would have collapsed too quickly. The strong anthropic principle goes further, suggesting that the universe must have properties that allow for life to emerge, or that intelligent observation somehow brings the universe into being. While the weak anthropic principle is a statement about selection effects, not a fundamental explanation, it becomes particularly compelling in the context of the multiverse hypothesis. If there are countless universes, each with randomly distributed physical constants, then it's not surprising that we find ourselves in one with just the right conditions for life, including a finely tuned value for dark energy. The eerie silence of dark energy's precisely balanced strength thus becomes a profound statement about our very existence, forcing us to consider whether our presence is a cosmic coincidence or a clue to a far grander, more diverse reality. It's a philosophical adventure that challenges our assumptions about uniqueness and destiny.
Our cosmic journey through the eerie silence of dark energy's impact has brought us face to face with the universe's most profound mystery, the mysterious force silently shaping its destiny. We embarked on this adventure from the initial shocking discovery in 1998 when astronomers, using Type 1a supernovae as cosmic beacons, found not a decelerating universe, but one that was accelerating, propelled by an unseen hand. This revelation launched us into a new era of cosmic exploration, revealing that this universal enigma accounts for a staggering 68% of the universe's total mass energy content, profoundly outweighing ordinary matter and even dark matter. We've delved into the leading candidate for this pervasive influence, the cosmological constant, a concept Einstein once regretted, but which now stands as the simplest explanation for the accelerating expansion. Yet we grappled with the profound theoretical challenge it presents, the cosmological constant problem, a staggering mismatch between quantum predictions and observed reality. This led us to explore alternative models like quintessence, a dynamic field that could evolve over cosmic time, potentially altering the universe's ultimate fate. We saw how this cosmic accelerator has subtly yet dramatically influenced the formation of the cosmic web and the growth of structures like galaxy clusters, acting as a cosmic anti-glue.
Our quest highlighted the intense observational efforts underway, from the Dark Energy Survey and the Euclid mission, to DESI and the Vera C. Rubin Observatory, meticulously mapping billions of galaxies, probing gravitational lensing, and measuring baryon acoustic oscillations to decipher the properties of this elusive force. We confronted the Hubble tension, a persistent discrepancy in the universe's expansion rate that hints at new physics and reminds us that our standard lambda CDM model, while highly successful, may still be incomplete. And finally, we peered into the distant future, considering the universe's potential fates, the Big Freeze, a gradual descent into eternal cold and emptiness, or the more dramatic Big Rip, where the very fabric of space-time is torn apart. Each scenario, dictated by the subtle nuances of dark energy, carries profound philosophical implications for humanity's place in the cosmos, prompting us to contemplate our significance in a universe dominated by an unseen, incomprehensible power. The eerie silence of dark energy's impact is not just a scientific problem, it's a cosmic drama unfolding on the grandest stage imaginable, a mystery that could dictate our cosmic destiny. It challenges us to question, to explore, and to embrace the vast, humbling unknowns that define our universe.
Our journey to decode the universe's silent force is far from over. This cosmic mystery continues to inspire new questions, new missions, and new theoretical frameworks. It is a testament to humanity's enduring curiosity, our relentless drive to understand the cosmos we inhabit, no matter how strange or challenging the answers may be. As we continue to listen to the whispers from the void, we hope to eventually break the eerie silence of dark energy and unlock its profound secrets. If you've been captivated by this cosmic adventure and want to continue exploring the universe's greatest mysteries with us, be sure to subscribe to join us for more cosmic adventures.